Hi, my name is Matthew Zong, and this is a presentation for a C++ robotics simulator I wrote in 5 days. Let's first begin by discussing what my simulator can do. My simulator can analyze for any kinematic chain the following: forward kinematics, forward differential kinematics, inverse differential kinematics, and the end effector and joint reaction statics. Let's take a look at each of these features one by one. We begin by analyzing the forward kinematics of a 6-joint manipulator. We can tweak each joint position to observe how the end effector changes. To see how the DH parameters change, take a look at the table at the top. Using the left mouse button, here's what happens when we tweak joint 1, joint 2, joint 3, joint 4, joint 5, and joint 6. Notice how the end effector changes intuitively as each joint is manipulated. We next analyze the forward differential kinematics of our manipulator. Internally, this program uses a finite difference representation of a Jacobian matrix to compute the end effector velocities, governed through the following formula. Consider what happens when we manipulate the velocities of each joint. Notice how the end effector velocity changes as we manipulate Q'1, Q'2, Q'3, Q'4, Q'5, and Q'6. Additionally, notice how changing joint positions also changes the end effector velocity as appropriate. In my simulation, deriving the inverse differential kinematics only considers the linear end effector Jacobian. I wanted to add angles, but the simulation never worked properly with them, sadly. So, whoops. Because I'm working with so many joints, and because the Jacobian augmented matrix I derive has more columns than it has rows, I'm bound to have some free variables, as determined through my simulation. By specifying additional constraints in these variables, I can derive the required joint velocities for the other joints, as I'm showing in this example. As expected, adjusting the required end effector linear velocity imposes its own set of joint velocity changes. Finally, notice how changing the manipulator orientation also changes the velocities as expected. This simulation supports analysis of a force and moment applied to the end effector. We can see that when we transform this couple to the base frame, while the force moves directly, the moment changes based on the end effector position. Finally, using the inverse of the Jacobian as I have derived before, we can compute the joint reactions for each joint as appropriate.